the newest contest problem, 2492, minimum score of a path between two cities. So let's go ahead and get right into this problem. So you're given a positive integer n representing n cities number from 1 to n. You're also given a 2D array roads where roads I equals ai, bi, distance I, which indicates that there's a bidirectional road between cities ai and bi with the distance equal to distance I. The city's graph is not necessarily connected. Okay, so there's a system of cities. They're connected by roads. There's weights between each city. So this can easily be modeled with a graph, a bidirectional graph, right? If there's an edge between A and B, there's a corresponding edge between B and A, and it's not necessarily connected. So you can't necessarily go from one city to another city. There's connected components within this graph. The score of a path between two cities is defined as the minimum distance of a road in this path. Okay, so this is a weird idea, right? So I guess the cost of doing something is just the minimum cost of any edge in that path, right? So even if it's like a super long, treacherous path to get from source to a destination, the score is only the minimum path road that you had to take. So that kind of eliminates some notions we think of when we do, traversal problems and trying to find minimum paths. Return the minimum possible score of a path between cities 1 and cities n. Okay, a path is a sequence of roads between two cities. That makes sense. It is allowed for a path to contain the same road multiple times. You can visit cities 1 and n multiple times along the path. The test cases are generated such that there's at least one path between 1 and n. Okay, so there's a few points, some intuition that we can gain from each of these notes, which is going to greatly affect how we approach this problem. If you can use the same road multiple times, then it's only going to benefit you to try to find the minimum road that you can reach, right? So I guess the best way to describe this with an extreme example is, let's say that you had a path. Sorry, I'm going to open up my tablet here. Go Bears. All right, so let's imagine that you had a path source, destination here. We'll just start here. I'm having some difficulties. To go from 1 to n, you start at 1, and your nth value would be 4. Now, obviously, the shortest path in like a traditional approach would be going directly from 1 to 4 with cost 7. But since the cost is defined by the minimum edge within this path, would actually be kind of optimal to go from 1 to 2 and then 2 to 4, or even 1 to 4 and 4 to 2, then back to 4, right? Because really the approach of this problem isn't trying to find the minimum path between a source and destination. It's just trying to find the minimum edge that you can reach, right? Because if the test cases are generated such that there's at least one path between 1 and n, then you know for sure that from 1 you can reach n, right? So wherever you start, you're definitely going to be able to get to the destination at some point, right? Since you're definitely going to be able to get to the destination at some point, your objective isn't to get to the destination then, because you know that can occur. So your objective really is to find the minimum edge that you can traverse, right? The minimum road that you can traverse to determine the minimum cost that you can reach. And kind of an extreme example of that to better establish that point, if you had a system like an n equals 4 example like this, right? In this system, okay, if our objective is to get from 1 to 4, where there's an invariant that it's definitely connected, meaning that there's always a path from 1 to 4. Now, let's say that these edges had cost 8, 9, and 1. Now, there's definitely a path from 1 to 4, the way the system's set up. So, obviously, you can go from 1 to 3 and 3 to 4. But since you can visit the same road numerous times, there's no reason not to also take this additional path from 1 and then back down. Right? So, the point is you have a system of nodes that are connected. You can definitely always get from your source to a destination. So your objective should then be just to find the road path that you can reach that's minimum. Now, then you may argue, well, since I can reach all roads and I know I can get to the destination, I might as well just look at the input system and find the lowest weight in that graph. But since the city's graph is not necessarily connected, it's possible, right, if we were looking at this example again, it's possible you'd be put in a scenario where you have perhaps additional system here. So let's call this 6. So imagine that 6 was the last node, and then you had a different set of connected components. 5 and 4 here, and this had cost 0 associated with it, right? So in this system, if you were just looking at all the roads individually, you'd say, well, the minimum road is 0. But it's not necessarily true that you can reach all the nodes in the system, only that you can reach the destination node in the system. So you can definitely reach the destination node, but you can't be confident that you can reach every road in the system. So your objective would be just to find the minimum road within the connected component of which you're connected to. So the easiest way to do that would be to traverse this system. So you'd start at the connected node and either run some sort of traversal algorithm like depth first search or breadth first search and find the minimum road that you can reach. Of course, it's going to be a little tricky because, you know, there's systems where there are cycles, so you don't want to have a recursive infinite loop. So you just want to ensure that you don't, just ensure that you keep track of everything that you're seeing. So we're just going to run an example of DFS, right? So we'll have a scene array, we'll call it S. And this will just be used to keep track of nodes that we've already visited. And then we'll just have an example of DFS. Well, actually first, when we look at this roads, right, it's given as this adjacency list. So we should probably represent the system as a graph because it would be easier to traverse the system and more efficient that way. So we'll create an adjacency list for each of the possible nodes. I'm doing n+1 here because the system starts at 1, so we have to do a 1 offset. And then we'll look at each UV pair. So city U, city V is connected with the road R with weight W. So we'll look at each road and we'll say, okay, well, G, the city U has a path to city V with weight W. And since it's a bidirectional graph, G of V also has a path to U with weight W as well. And then we'll just put this on one line because whatever. Okay. We can also put this on one line. A shorter solution, easier to sell. Okay. So how are we going to run DFS here? Well, what we're trying to do is just find the minimum road for any node, right? Well, if we've already looked at a node, that means we've already considered all roads connecting to it. So we don't need to consider it again. So we'll just return float infinity. This will just keep us from recomputing information that we've already found. If we get to this point, line 11, that means that this was false. So we haven't seen this node yet. So let's set it as seen so that we don't traverse it again. And then all we have to do is return the min. Well, the minimum of what? Well, we're trying to find the minimum road, right? So I'll look at the minimum road for all my neighbors. So for all my neighbors, just trying to think of the best way of doing this. So we'll have a float infinity. So the idea here is to, as you traverse to a node, keep track of how much you spent to get here, what the road cost was. So you can easily say, well, the minimum cost, let's look at this example before I write down the corresponding code here. So example 1 gives us 1, 4, 2, 3, right, cost associated 7, 9, 5, 6. So if we ran DFS on the system, we'd first enter in at 1, and we're just trying to find the minimum cost road within the connected component that 1 is connected to. It just so happens in this system that there's just one connected component. And, well, to find the minimum, we can go here and keep track of what was sent in, which is 7. And then 4 will return the minimum of, well, what it costs to go into it, because that's one road, and the minimum from nodes that it can access. Right? So 4 is going to say, here's the cost of the road you used to get to me, and the minimum cost of whatever system comes after me. So if we just keep following through here, this will go to 2, and 2 will have access to 5. This will go to 9. But this has already been traversed, so it would return infinities, but it should return 9. So that means that this instead should return the W value that the path took to get here, because that's an additional road to consider. So we want to take the minimum of, well, W of the path going in here, plus DFS for each neighbor, V, and the cost of going to V, so the weight of V, for V, weight of V in the graph at node U. So this will give us the minimum. So the minimum of the cost to get to this node and any node I can reach in the system. This will ensure we don't do loops. And so at the end, we just return DFS of what? Well, we know we have to go from 1 to n, but since we can take any road, we just want to find the minimum of the connected component that includes 1, because that'll be the same as the minimum component of n. So we could do DFS from 1 or n, but it has to be either 1, and I guess 1's a little more intuitive. Okay, so we run this. Okay, so I called this scene here and S here. Let's run that again. For some reason, I've been running into a strange bug with Leetcode where it will randomly sign me out. And I'm not sure what's causing that. So if any of you have any sort of understanding to what that is, then please comment below. You gotta be kidding me. I'm gonna try opening it, and now it works. Okay, so let's go ahead and submit that. Okay, so I'm gonna have to cut the video here because there's something wrong with the Leetcode, but that is the all right. It loaded just in time. Let's see. Okay. All right, there you go. Now, of course, this faster than 95% of solutions, faster than 100% of solutions is not exactly um, the most reliable answer, right? Because this is a new competition problem. There hasn't been enough submissions to, you know, eliminate the large amount of variance between each attempt, right? There's only been like 8,000 accepted solutions. So don't think because your answer is like this that, you have the optimal approach. So what is the runtime and space complexity of this problem? Okay, well, time complexity, we look at each node and we look at each node once. Um, for each node, we have to look at each road that connects to it. So if n is the number of cities and m is the number of roads, that's linear with respect to that. And then in terms of space, well, we have to create a graph with each node, and for each node, we have to add a reference for each road that's connected to us. So we'll again have O of n plus m space. All right, cool. Thank you.